Hi everybody, this is Dr. Bricker here with some hints for homework number 10, which covers Chapter 13. Chapter 13 is about fluids, both fluid statics and fluid dynamics. So let's take a look at this. First problem, we have a 68 kilogram college student. Density is given, 1,050 kilograms per cubic meter. What is the volume? So you probably have seen this kind of problem going back all the way to like 6th grade or something like that, but let me just refresh your memory about this. Okay, so density is mass divided by volume. So we're trying to figure out the volume in this problem, so a little bit of algebra. Volume then would be mass divided by density. And if you notice, I use this big V for volume instead of little v. We'll do some problems in this chapter which involve volume and velocity, and it can become really confusing. So this symbol, it's not P, it's rho. We also have pressure in this chapter, so don't write P for this. You might get confused. So rho, mass over volume, kilograms per cubic meter. That's the SI unit. So in this problem, you're given the mass and you're given the density. You'll see that the volume will come out in kilograms cubed. All right, let's look at the next one. Okay, so fat cells in humans are composed almost entirely of pure triglycerides with an average density of about 900 kilograms per cubic meter, so less than water. If 20% of the mass of a 70 kilogram student's body is fat, what is the total volume of fat? Okay, so without putting any numbers in it, 20% of 70, so that would be 14. 10% of 70 would be 7, so this is 20%, making it 14. So we've got 14 kilograms of fat. We know the density of fat here. So if you know the density and you know the mass, you can figure out the volume. Really similar to the previous problem. Okay, moving right along to the next one. The deepest point in the ocean is 11 kilometers below sea level. Deeper than Mount Everest is tall. What is the pressure at this depth? So with pressure, you've got to be careful. They want the answer in atmospheres. So if you imagine you go deeper and deeper into the ocean, the pressure gets larger and larger because of all that volume above you. So let's actually calculate this pressure. Okay, so here's the top of the ocean. This is just atmospheric pressure. So atmospheric pressure, 1.01 times 10 to the 5th newtons per square meter, or you could say 1.01 times 10 to the 5th pascals. A newton per square meter is a pascal. So that's 1 atmosphere. Okay, and then we want to figure out the pressure here at this depth. And the depth here is 11 kilometers, so 11 times 10 to the 3rd. So what are we going to use for the density of water? It's an ocean, so I'm going to use the density of salt water. And this is in a table in the chapter. So the pressure at depth is the pressure at the top plus rho times g times y. So you know this, we're assuming this is atmospheric pressure, 1.01 times 10 to the 5th. And then we have rho, which we know because it's seawater, times g times y. So let me do one more step here. When you put this all together, we have all the information here. Pascals, 1,030 kilograms per cubic meter times 9.8. I'm running out of room. Meters per second squared. And then times 11 times 10 to the 3rd meters. You'll get this answer, and it will be in pascals. If you notice, this part will come out in newtons per square meter, kilogram meter per second squared, and then per square meter. This will come out in pascals. And then you'll have to turn it into atmospheres, and here's the conversion factor. 1 atmosphere, 1.013 times 10 to the 5th pascals. Okay, let's look at the next one. Okay, so we have a container of gas here. This is mercury, and this is open to the atmosphere. and we want to know what is the gas pressure inside the box that's shown. We've got a few different dimensions here. So now you have to imagine if the pressure of the gas was greater, that would push the mercury this way. So the atmospheric pressure is open here. The atmosphere is pushing mercury this way. Gas pressure is pushing mercury that way. Atmospheric pressure is actually winning, right? Because this is pushed down farther. This level here is lower than this level here. So the pressure of the gas is going to be less than the atmospheric pressure. If the pressure of the gas were more, this is the other way of looking at it, this would push mercury this way. And that's not what's going on. One thing that we do know is the pressure at this level is the same as the pressure at this level. Okay, so when you have a fluid like this, like mercury, and you have a height here and a height here, the pressures have to be the same. If they weren't the same at this same height, then the fluid actually would be moving, and it's not. Okay, so let's sketch this out and solve this problem. This is something called a manometer. Okay, so here's the picture we have. A few different dimensions were given. This was 6 centimeters. This whole thing was 16 centimeters. So now I know that this must be 10, right? From this point up to here, because this is 10, we have another 6. I know that the pressure at this point is just atmospheric pressure. So why don't I just call this one like P1 or something. It's open to the atmosphere. That's 1.01 times 10 to the third pascals. And then this is at the same level, so I know it's got to be the same pressure. This pressure is also 1.01 times 10 to the third, or 10 to the fifth. I think I said third, but I meant fifth. 1.01 times 10 to the fifth. 1.01 times 10 to the fifth pascals. So I know that this pressure, I called it P1 over there, I'll just call it P1 over here. The pressure here is equal to the pressure here plus rho GH of this column. So let me write out what I've just said. P1, pressure at depth, is equal to the pressure at the top, that's the gas pressure, plus rho GY of this column. Just like we did with the ocean problem, the pressure at the bottom of the ocean was due to the pressure at the top of the ocean plus rho GY. It's the same thing here. The pressure here at depth is equal to the pressure at the top plus rho GY. This is the Y I'm talking about, the 10 centimeters. So rho GY. You have to do a little bit of algebra to solve for the gas pressure, but you can do that. You know this. It's mercury. Look it up in the book. I've already done that for you, actually. 13,600. G is 9.8. Y is 10 centimeters. Just be careful. Put that into meters, right? So 10 centimeters, there's 100 centimeters per meter. Okay, so a little bit of algebra solve for the gas pressure. All right, moving on to the next one. Okay, so we have hippos spend most of their lives in water, but amazingly they don't swim. They have, like manatees, very little body fat. The density of a hippo's body is 1,030. So actually the density is greater than fresh water and similar to salt water. So it sinks to the bottom of a freshwater lake. Okay, so the density of the hippo is 1,030. Density of water is 1,000. So more dense, sinks to the bottom. So it sinks to the bottom of a freshwater lake, lakes and rivers it frequents, and then simply walks along the bottom. So the hippo feels lighter because you've got a buoyant force pushing up and weight pulling down. So the buoyant force helps out. A lot of these problems with the buoyant force are similar to what we did in chapter 4 and 5. It's just now we have a new force we can play around with, something called the buoyant force. Okay, and there's a picture of a hippo running around at the bottom. So here's the density of the hippo. We've got a 1,500 kilogram hippo is completely submerged, standing on the bottom of a lake. What is the approximate value of the upward normal force on the hippo? Okay, so if the hippo were not in water, the normal force up would be equal to the weight that's down. The difference with this problem is now we have this additional force up, something called the buoyant force that we can play around with. So taking into account that we have the buoyant force, how much would the normal force have to be? So we'll need a free body diagram. All right, let's take a look at that. Okay, so as far as the free body diagram goes, we have the weight of the hippo, that's this way, and that's equal to mg. Upward, we've got the normal force, but we also have this new force called the buoyant force, so both of those are up. That allows the normal force to be less than it would be if we're just in air. So we've got buoyant force up plus the normal force up is equal to the weight. Okay, so the buoyant force, that's the new thing from this chapter. This is the density of the fluid, volume of the fluid that is displaced, and times g. So let me say this again. So the buoyant force is the density of the fluid, and we're just in water, so the density of the fluid is 1,000. The volume of the fluid that's displaced. So when the hippo is completely underwater, the volume of the fluid that's displaced is the same thing as the volume of the hippo. So if you put something and it's completely submerged, say you put a baseball, and you know the volume of a baseball, you put it into a beaker, the volume displaced, in other words, the volume that goes up in the beaker would be the same as the volume of the ball that you put into it. So in this example, the hippo is completely submerged, so the volume of the hippo is the same thing as the volume that's displaced. Now if you took an object and you only submerged it halfway in a fluid, then you would just use half of the volume of the object, because the volume of the fluid displaced would just be half as much. Okay, so this is the new part here. This is old. Free body diagrams, balancing forces. This is new, this new force that we've had called the buoyant force. Okay, so weight is mg. We're given the mass and we know what g is. This is what we're trying to figure out. Let me just do one more step of algebra before we move on. Normal force, weight minus buoyant force. So the weight would be mg. The buoyant force would be the volume of the fluid. Density of the fluid. Volume of the fluid. So how are you going to get the volume of the fluid? Well, the volume of the fluid is the same thing as the volume of the hippo because it's completely submerged. So you have to do a little bit of algebra to do that. So we'll get the volume of the hippo. You can do that though because you know the density of the hippo and you know the mass of the hippo. So figure out the volume of the hippo and then times g. Okay, and then you'll see the normal force. Obviously it's got to be less than mg. Now if you're not submerged, this part goes away and then the normal force is just equal to mg. But here you've got this additional force helping you out, the buoyant force. Okay, let's look at the next one. Okay, so this one actually has a video tutor solution. You can take a look at that. The author of the book can help you out. Remember, you can hit review here and go right to the exact section of the book that pertains to this sort of problem. So here we have a block of aluminum. Density of aluminum is given. The volume of the aluminum is given. Completely submerged in ethyl alcohol. And then we want to know what is the tension in the string. So if you imagine, the tension in the string would be less than it normally is. By normally, I mean if it was just hanging in air, there would be a certain amount of tension. But here, you have the buoyant force helping out. So let me just kind of sketch out the free body diagram for this one. Alright, so similar to the hippo problem actually, it's just instead of there being a normal force up, we have tension that's up. That's the free body diagram, but so we know that the tension plus the buoyant force has to be equal to the weight, to mg. So then the tension is mg minus the buoyant force. So you can see it's really similar to what we did before. Now the buoyant force is going to be the density of the fluid. You'll have to look up ethyl alcohol in the book. The volume of the fluid that's displaced, well, turns out to be the same thing as the volume of the object again, the aluminum, and then times g, right? Because it's completely submerged. This and this are the same thing. Okay, they don't actually give you the mass of aluminum directly, but they give you the density and the volume, so you can figure out the mass. One thing to be careful of is 100 cubic centimeters. That's not an SI unit. we want to turn that into cubic meters. Be careful, you don't just divide or multiply by 100. You have to look at it like this. 1 cubic meter would be 100 centimeters times 100 centimeters times 100 centimeters. So to put 100 cubic centimeters into cubic meters, you actually have to divide by 3 times, right? Because 1 cubic meter is 100 times 100 times 100 cubic centimeters. Okay, but then you have all the information after that to figure out the tension. All right, let's look at the next one. Okay, so the first part of the chapter, and really the first 6 questions, dealt with fluid statics, fluids not moving. The last 4 questions deal with fluid dynamics. So as far as chapter 13 goes, I didn't do anything with turbulent flow, so everything is a nice streamline flow. You'll see that there's a little bit at the end of the chapter about viscosity and things like that, but I didn't include viscosity. I went with the very general laminar fluid flow. So don't worry about viscosity. Viscosity is basically friction when water moves, like something like molasses would have a viscous force. We're not worried about that. We're worried about nice clean flow, not turbulent flow. So we go through the Bernoulli's force section, but after that we stop. Okay, so let's look at what we have here. Your low flow shower head is delivering 1 times 10 to the minus 4 cubic meters per second. So that's how many volumes per second. That's about 1.6 gallons per minute, just as a reference. If this is the only water being used in your house, how fast is the water moving through your house's water supply line, which has a diameter of about 3/4 of an inch, or 0.021 meters? Okay, so given this volume flow rate, how fast is the water going through a typical pipe? Okay, so let's look at volume flow rate. Okay, so here's a piece of pipe. Here's the cross-sectional area of one side, so it's kind of like a cylinder. Water's flowing through here. So here's the area, here's some dimension x. If I wanted to figure out the volume here would be the area times x. If I want to know the volume per time, I could just divide both sides by the time. So this is the volume flow rate. It's called Q here. So volume flow rate is Q, volume per time. And then area, and then x over t is the velocity. So if you're wondering why volume flow rate is area times velocity, you have to think of the velocity as being this distance, and then divide the whole thing by time. The part that's changing is the x part. So we could identify that as x over t as the velocity. So this is why this is little v for velocity. This is big V for volume. It can be confusing, so you have to keep track of those things. Okay, good. So in this problem, I believe that they gave us the volume flow rate, and we want to figure out the velocity. How much is the velocity? They don't give us the area directly, but we have to assume the pipe has this kind of a shape. So you can figure out the area. Pi r squared or pi d squared over 4. So volume flow rate's given. You'll have to do a little bit of work to get the, volume flow rate's given, do a little bit of work to get the area, and then solve for the velocity. Okay, let's look at the next one. Okay, so in this one we have a 1 centimeter diameter pipe, widens to 2 centimeters, then narrows to 1/2 centimeter. Liquid flows through the first part at 4 meters per second. What is the speed in the second part? What is the speed in the third part? Okay, so the thing to think about this is something called the continuity condition, continuity equation. The volume that's coming out of the pipe cannot change. Whether it gets thinner or thicker, it's the same volume that's coming out. Now when you take the pipe and you scrunch it down and make the area smaller, like if you had a hose and you put your thumb over the end, it's the same amount of water that comes out, but if you put your thumb over the end, you make the area smaller, so you make the speed greater. So you might think it's directly proportional to the size, but it's not. So let me show you why it's not, and we can solve this problem. Okay, so here's the pipe. We've got 1 centimeter, and we know it's going at 4 meters per second. Now the pipe gets twice as big, up to 2 centimeters. So you might think that the speed is just cut in half, but it's not. and you'll see why in a minute. And then here it goes from 1 all the way up to 2, but then back down to 0.5. And we want to know the speed here and the speed here. Again, the thing that's not going to change is the volume flow rate. The Q is the same. It's the same amount of volume per time. Same amount of cubic meters per second. So the way I could do this, I'll just call this one V1. V1 times area 1, it's got to be equal to V2 times area 2, that's V3 times area 3. Because the volume flow rate doesn't change. Now, remember the area, let me take another step here. This would be pi diameter 1 squared over 4. This would be V2, and then the area would be pi diameter 2 squared divided by 4. Remember, it's the area of a circle. This would be V3 pi d3 squared over 4. The pi's and the 4's all cancel out. So I've got this situation where I've got V1 diameter 1 squared. That's got to be equal to V2 diameter 2 squared. That's equal to V3 diameter 3 squared. Okay, so you know all the different diameters. 1, 2, and 3. So if you wanted to get V2, you could use this part of the equation. You know V1, you know D1, D2. The only thing that you wouldn't know is V2, so you can do that to solve for V2. Same idea here. You know this and this have to be equal to each other. The only thing that you don't know is what you're looking for. Or if you want to look at it like this, this is squared and this is squared. So if this is twice as big, because of the relationship between D1 and D2, that it's squared, if this diameter is twice as big, the speed's got to be 1/4 as much for the equality to hold true. Same thing over here. If I'm comparing V1 and V3, if the diameter is half as much, when I square it, that means that the speed's going to be 4 times as much. So if I had 16 here, sorry, thinking ahead already. If I've got 4 here and I cut the diameter in half, this has to be 4 times greater, so this would have to be 16 there. So you could do it the first way I said, more mathematically rigorous. Just take this equation, this and this and this, you can solve for V2. Or for the part B, this and this and this, you can solve for V3. Or you could realize the relationship between the way that it goes, that D1 squared and D2 squared. So making it twice as big makes the speed 1/4 as much. Okay, so that was a volume flow rate problem. Let's take a look at the next one. Okay, so during typical urination, a man releases 400 milliliters of urine. Okay, that's a perfectly good unit. It's just not an SI unit, so you'll have to turn that into cubic meters. It'll be a really small amount of cubic meters in 30 seconds. So that's really the volume flow rate, 400 milliliters in 30 seconds, but just make sure that you put that into SI units. Convert milliliters into cubic meters. You'll have to look up the conversion factor. Here's a nice place to start this review section here. Which can be modeled as a tube 4 millimeters in diameter and 20 centimeters long. Assume that the urine has the same density of water, so 1,000 kilograms per cubic meter, and the viscosity can be ignored. Okay, so no sort of friction associated with the fluid. What is the flow speed in the urethra? So what's the flow speed in this tube? And then part B, if we assume that the fluid is released at the same height as the bladder and that the fluid is at rest in the bladder, which is a reasonable assumption, what gauge pressure in the bladder could produce this flow? Okay, and the gauge pressure is the difference between the bladder pressure and atmospheric pressure. Okay, so it's a volume flow rate problem. In addition to that, it's a Bernoulli's equation problem. Good, so let's take a look at that. Okay, so we've got 400 milliliters in 30 seconds. I looked up the conversion factor. 1 milliliter is 1 to the minus 6 cubic meters. So you could figure out the volume flow rate from this. Put that into cubic meters, 30 seconds. You can figure out the volume flow rate. And then you know the volume flow rate from what we were just talking about. It's area times velocity. So the velocity then, like we've done before, volume flow rate, which you'll have to do some work to get, divided by the cross-sectional area. Same thing like before. Pi d squared over 4, or if you want, pi r squared. They give you the diameter, so I just left it in terms of the diameter. So then you can get the volume flow rate, no problem. Similar to what we've done before, it's just you have to do more work for Q, you've got to do more work for the area again. But then you can get the speed here. The second part is, what is the bladder pressure minus the atmospheric pressure? So we're going to assume that this is a tube and it's horizontal. So here you've got the pressure of the bladder, and they tell you that the fluid starts at rest. So initially there's no speed. Here, this is open to the atmosphere, and then this is the speed that you found in the first part. So this speed is what you found in the first part. So you go from nothing to something, there has to be a difference in pressure. The pressure here has to be bigger than the pressure here. Okay, so let's actually use Bernoulli's equation to solve this. Okay, so you got to look at what's going on here and look at what's going on here. So it's a horizontal tube, there's no change in height, so we don't have to worry about that part of Bernoulli's equation. But we have pressure at the bladder plus 1/2 the density of the fluid, velocity of the bladder squared, that's the kinetic energy term. So pressure, this would be the kinetic energy term. There would also be gravitational sort of potential energy term, but it's the same here and here, so we don't have to include that. So this is what's going on here. This would be equal to pressure atmosphere plus 1/2 rho v squared. And this is the v again that you figured out in the first part. And we're trying to figure out the difference between bladder pressure and atmospheric pressure. So we don't have to figure out this and this independently. We just want to know the difference. Bladder pressure minus atmospheric pressure. That's what they're asking about. So I'm subtracting this from both sides. That would be equal to 1/2 rho v squared minus 1/2 rho v bladder squared. And actually they tell you that this starts from rest. So that term goes away. So after all that, the bladder pressure minus atmospheric pressure turns out to be 1/2 rho v squared. And again, they say model this as being water, and the v comes from the first part. It's actually more complicated than this. It's not completely just reliant on differences in pressure. There's more going on physically, but this is a good place to start to figure out that difference in pressure. Alright, let's look at the final question. Now you see with this problem in the picture, this actually has a difference in height. The previous picture, it was just a horizontal tube, but here we've got like a kinetic energy type term. Here we have a, because there's some height here, we've got a gravitational potential energy sort of term. And we want to know what is the pressure up here. Now the volume flow rate equation still works. So if you have, if you know the volume flow rate here, it's the same as the volume flow rate here. Fluid is just coming out faster at the top because it's more constricted. And then be careful, we want the answer in kilopascals. Okay, so not a lot of information given here. You've got to rely on the picture to figure out how fast things are going. Okay, so let's put this on paper. Okay, so here's the picture. So keep the picture in mind again when I show you these numbers. So with Bernoulli's equation, we've got P1 plus 1/2 rho V1 squared plus rho GY1. That's the beginning of the pipe. That's got to be equal to P2, the pressure up there, plus 1/2 rho V2 squared plus rho GY2. There's a lot of parts to this, but you just have to keep track of them. It's not that it's hard to do that. It's just cumbersome, maybe. So y1 was 0. This term actually goes away. And then the only thing that you do not know is what you're looking for, which is P2. This is what you're looking for. You want it in kilopascals. So let me just do one more step. P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. That's what V2's got to be equal to. Oh, I think I skipped it. I skipped one. Minus rho GY2 is equal to P2. Okay, make sure I did this right. P1, so pressure 1, 1/2 rho V1 squared. Okay, that's good. That term is 0. And then subtract this from both sides, 1/2 rho V2 squared. Subtract rho GY2, and that gives you P2. So you have everything. Just make sure that you put this as 200 times 10 to the third pascals when you add it to all these other SI terms. And then you've got to convert the final answer. So dot, 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 get the final answer. It'll be in pascals. Convert it to kilopascals. All right, if you have any questions, let me know, and I will talk to you later. Bye-bye.